Okay, so we're going to go through some binomial distribution examples. So what we have is, let's go through example number 1. You have 13 kumquats, and we'll say that 85% of kumquats in general are fresh. So what is the probability that exactly 10 are fresh? And so so we're going to kind of lay out our thing here. We're going to have success, N, P, Q, X. And generally you could fill this, if you fill this out correctly, the problem is pretty much done because then you're just plugging it into a formula. Most people, of course, don't fill it out correctly. The line that you mix up the most actually is usually the success one. But you'll discover that for yourself. So what are we going to call success? So success in this case is going to be that a kumquat is fresh. When I say success, I don't mean what is, like, it might be tempting to say success is that 10 are fresh. No, that's how many successes we're looking for. That's going to be our X. Success is how we're defining success for a single trial, not for the whole thing, for a single trial. So we're going to say that a kumquat is fresh is a success. The number of trials is 13. The probability of success being defined as the kumquat is fresh is going to be 85%. The probability of failure is 15%. How many are we looking for? We're looking for 10 of them. And again, you should always probably write this down. So what it's going to be, the probability that x equals 10 is going to be, and choose x, p to the x, q to the n minus x, which is 13 choose 10, 0.85 to the 10, and 0.15 to the 13 minus 10, which would be 3. So then we're going to calculator this, because I'm not doing that in my head. So 13 choose 10 times 0.85 to the 10 times 0.15 to the 3 is 19, almost exactly 19%. So it's going to be 19.0%. And there we go. That's the probability. Okay. Example number 2. You have a 20% probability of missing a free throw. What is the probability you will miss exactly 3 out of 11 throws? So what we're going to do is we're going to, again, lay it out. Success, N, P, Q, X. So what have we got? The number of trials. Oh, wait, actually, what's a success? So it's not really clear. You know, we'll do it twice. We'll actually do it in 2 different ways. We'll do it in 2 different ways. So we'll have N, P, Q, X. So let's say, we could say that success, remember, success doesn't have to, we could say that success is miss a free throw. So success is going to be miss a free throw. So now how many trials do we have? We have 11 trials. The probability of success is the probability of missing is going to be 0.2. The probability of not missing is going to be 0.8. And the number of successes being missing a free throw, is going to be 3. Now what we could have done, so essentially this is kind of like an OR. one of these two things. We could have defined success as the opposite of missing a free throw, I guess. Sinking the basket. I'm not sure what the proper term is. Sink the basket. So we changed the definition of success, but now we have to figure out what our variable, what the value of our variables are. So the number of trials is still going to be 11, but now success is going to be sinking the basket. So if there's a 20% chance of missing, there's an 80% chance of sinking the basket, and a 20% chance of not sinking the basket or missing it. Now, how many successes are we looking for? If we're looking to miss 3 out of 11, then we're looking to not miss 8 out of 11. So the x would be 8. So if we went and if we went ahead and calculated this now, let's bring this up a little bit. So what we're going to have over here, we have the probability that x equals 3 is 11 choose 3, 0.2 to the 3, 0.8 to the 11 minus 3, which is 8. Or if we did it over here, we'd have the probability that x equals 8, which is going to be 11 choose 8 times p to the x times q to the n minus x, 11 minus 8, which would be 3. And if you look, they're kind of the same, right? Here we have 0.8 to the 8, 0.8 to the 8, 0.2 to the 3, 0.2 to the 3, and it turns out 11 choose 3 and 11 choose 8 are also the same. If we actually do it in, 11 choose 3 times 0.2 to the 3 times 0.8 to the 8. And that's going to be 22.15%. So either way, the answer is going to be 22.15%. And if you did it over here, it would also be 22.15%. Okay. Now, let's do a harder one. So what we're going to have here is we're going to have an assembly line makes engines. But they do it badly, so it's one of those, maybe I shouldn't say the name of the company publicly. One of those companies that makes engines badly. So we'll say that 2% of them are fatally flawed. So they go kaboom. 50 engines are produced. What is the probability that at least 48 are not flawed? So assembly line makes engines, 2% of them are horribly flawed, 50 are produced. What's the probability that at least 48 are not horribly bad? So success N P Q X. I would probably pause the video at this point and try to figure it out yourself, and that will give you a better idea whether you could do it or not. So I'm going to say that success is that an engine is good. So the number of trials we have is 50. The probability of success, the probability of an engine being good, if 2% are bad, then 98% are good. The probability of it being bad would be 2%. Don't forget there's an extra 0 there. And we want at least 48 to be not flawed, so we want at least 48 to be good. So at least, remember, that's a code word for cases probably, or indirect at the very least. So that's going to be, we could have 48 or 49 or 50. So what are we going to have to do? Unfortunately, that means we're actually going to have to do that formula 3 times. There's not really a shortcut to that. So what we're going to have is we're going to have the probability that x equals 48. And that's going to be 50 choose 48 times 0.98 to the 48 times 0.02 to the 2. And then the probability x equals 49, which would be 50 choose 49, 0.98 to the 49, 0.02 to the 1. Probability x equals 50, which is 50 choose 50, 0.98 to the 50, 0.02 to the 0. It's just going to be 1. And we're going to calculate all these things now. So it's going to be 50 choose 48 times 0.98 to the 48 times 0.02 squared. So 18.6. So this one is 18.6%. And then for 49, it's going to be 50 choose 49 times 0.98 to the 49 times 0.02 to the 1, which is going to be 37.2%. And then this one is going to be, well, I'll do it anyway. 50 choose 50 is just 1, and that's just 1, so it's really just 0.98 to the 50. 0. And it's going to give us 36.4%. And so we want to have the probability that's at least 48 engines. It's going to be this or this or this. We add them together. And we get 92.2%. So the probability that at least 48 engines are not flawed is 92.2%. Now, I'd like to point out that we could have defined success in a different way, right? We could have defined success as, we could have said that success was engine fatally flawed. In that case, n would be, so we'd still have our npqx. Oh, let's say if I've changed the definition of success, what we have is, that would be 50 still. The probability of it being flawed, though, is 0.02. The probability of it not being flawed is 0.98. And the number of successes we'd be looking for here, we want at least 48. It's a little tricky to see. I'll kind of write this out. So this is number of good engines, and these are the bad ones. Right, so if we have 0, 1, 2, 3, 49, 50. So if we have 0 good engines, we have 50 bad engines. If we have 1 good engine, we have 49 bad engines. 2 good, 48 bad. If we have 50 good, we have 0 bad. If we have 49 good, we have 1 bad. If we have 48 good, then we have 2 bad. So we want at least 48 good. That's another way of saying we want at most 2 bad. So in this case, the x would actually be 0, 1, or 2. So we'd actually still have 3 cases. So changing what we call success does not actually change the number of cases. All it does is it changes the variables over there. So this would also come out to 92%. Okay. So let's say we're going to have a part B now. So it's a continuation of that first question. What is the probability that at least 2 are flawed? So usually what I do at this point is I give people a chance to go home and think about it a bit. But we're doing this in a different way, so we're not going to. But I would definitely promote pausing the video and trying to figure the NPQX yourself for this. Okay, so the n is still going to be 50. Well, let's say success is going to be flawed. We want at least 2 to be flawed. So the p is going to be that. The q is going to be, the p is going to be 0.02. The q is going to be 0.98. We want at least 2 to be flawed, so it has to be 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12 or 13 or, okay, this is getting excessive, but all the way up to 50. That's a lot of cases. So we're not going to do that. So obviously what we're going to do is we're going to change our definition of success. So we're going to change it to not flawed. And that will, of course, fix everything. So n is going to be 50 PQX. And I don't know why I put the 50 in black OS. So the probability of not being flawed is 0.98. This is going to be 0.02. And if we want at least 2 that are not flawed, another way of saying that is we want at most 48 that are good. So at least 2 that are not flawed is the same thing as saying at most 48. At most 48 good. So the number of cases here would be 0, 1, 2, 3, 4, 5, 6, 7. Okay. So that didn't actually save us a thing. Right? That's, if you remember one example back, when we had the first one, when we changed the definition of success, if we change the definition of success, it doesn't actually change the number of cases. All it does is changes the p's and the q's and the x's, but it's still going to be the same amount of work. So what we're going to do is we're going to bring back our old friend, indirect. So x is that. Not x, though, is going to be, so if x is 2 to 50, not x would actually be 0 or 1. So we want 2 to 50 flawed engines. That would be like not getting 0 or 1 flawed engines. Similarly, not x over here would be 49 or 50. So, yeah, and then we're going to go through the same thing. So now we're actually going to calculate it. So the probability that x equals 0 is going to be 50 choose 0 times 0.02 to the 0 times 0.98 to the 50, which we already did actually on previously in this example, which is 36.4%. And the probability x equals 1, we've actually already done that before as well. So that's 37.2%. I'm going to kind of skip ahead. So the probability of not getting what we want, so these are the bad cases, right? So these are both the bad cases. So the probability of getting what we want is going to be, so the good equals the total minus the bad, which is going to be 100% minus 36.4% minus 37.2%, which is 26.4%. So the probability of having at least 2 engines that are flawed, doing it indirectly, is going to be 26.4%.